Hello, calculus students, and welcome to this part 2 of trigonometric substitution. We're going to keep rolling here, converting the limits of integration. Now we have a radical that's in the numerator, and we're doing a definite integral. Now, your book recommends, and I guess it doesn't recommend, it just works through this example by converting the limits of integration, but I would argue there's a little bit more work involved in doing that, rather than just converting everything back in terms of x from theta, and then just using the original limits of integration. Okay, because when you do convert the limits of integration, if we were to keep things in terms of theta, then you have to take in some special considerations for values of theta you can and can't have. So I personally prefer just to convert back into terms of x and then just use the original limits of integration. So that's what we're going to do. You certainly can convert the limits of integration. Keep in mind that if you do that, you are going to have to consider those cases for the values of theta that were originally stated in those first three rules that we talked about at the beginning in part 1. That example is worked out using converting the limits of integration in the textbook, so if you want to do that, certainly go ahead. But we're just going to convert everything back in terms of the original variable x, and then use the original limits of integration. But we still need to kind of do the same technique. We want to set up our right triangle here, so let's go ahead and do that. And we want to eliminate this radical. So, well, it's involving x squared minus 3. That was a horrible triangle. Let me try that again. It's involving the square root of x squared minus 3. Well, we know that x squared is going to involve the hypotenuse. Our hypotenuse is going to be x. And then one of our legs is going to have to be, well, what squared is 3? And the answer is the square root of 3. And typically you use your constants. We're going to keep those same way we have. We're going to keep them here, which means that our other leg would then be the square root of x squared minus 3. Now we want to relate these two quantities to theta. It's going to involve a hypotenuse and an adjacent side, adjacent hypotenuse. We know that that's cosine, so cosine of theta is going to equal adjacent over hypotenuse, square root of 3 over x. Solve for x, you'd multiply by x and then divide by cosine. So you'd essentially have, I guess I'll just show the work here, x equals the square root of 3 over cosine theta. Well, we know that 1 over cosine is the same thing as secant, so x really is going to be the square root of 3 times secant theta. Again, if you have those things kind of memorized from earlier in the notes, you can certainly just know that it's going to be a times secant theta and use that. Okay, now we want to know what our dx is if we're going to substitute all these things and then integrate. Well, dx is going to be square root of 3 times what's the derivative of secant? And the derivative of secant is secant tangent, so we're going to have secant theta, tangent theta, and then our d theta. So we have everything that we want. We're going to plug this in. I'm going to treat this as if it's an indefinite integral, but just keep in mind we're using these limits of integration, root 3 to root 2. So we're going to do the integral of the square root. We're going to leave it as an indefinite integral, and then at the end, we're going to actually evaluate it. So let's just treat it as an indefinite integral right now. It's going to be the same process. Square root of x squared minus 3 over x dx. Okay, well, we know that this integral is the same as we can go ahead and plug in our values here. We know that, well, the square root, I guess we should go over that. The square root of x squared minus 3, if we were to plug in the cube root of secant theta, we would eventually get to the square root of x squared minus 3 is going to be the cube root of tangent theta. Okay, now that we have all the things we need, we're going to go ahead and plug them in. So we're going to have this cube root, this is equal to the integral of the cube root of tangent theta over, well, x we know is the cube root of secant theta. And then our dx is equal to cube root of secant tangent d theta. So we're just going to plug that in. That's this being multiplied in the numerator, square root of 3 secant theta tangent theta d theta. Some nice things are going to happen. We're multiplying everything in the numerator, which means if I'm multiplying by the cube root of secant theta and then dividing by the cube root of secant theta, those are going to reduce to 1. I'm going to be left with the integral of 3, this cube root of 3 times tangent theta again, d theta. Well, that's just going to be the cube root of tangent theta squared, or tangent squared theta, either way that's fine, d theta. Okay, now what we can do here is convert this using a trig identity, and we have that cube root of 3, that's a constant multiple, bring that out front. This is the same as the cube root of, use that Pythagorean identity. This is going to be the secant squared theta minus 1. d theta, which we can then do the antiderivative of. This is the cube root of, well, what's the antiderivative of secant squared theta? That's tangent theta. Tangent theta. Okay, and then minus, well, the antiderivative of -1 in terms of theta is going to be negative theta. Okay, now this is what our indefinite integral would be, but keep in mind, we want to do a definite integral, and we want to just use our original limits of integration, root 3 to 2. The form of that we're in right now, we can't just plug those in, because those limits of integration are in terms of x. So our goal then is to get this theta and this tangent theta in terms of x. Okay, well, what is tangent theta in terms of x? That one's easy enough to do. Just go up to the triangle. We know tangent theta is going to equal, well, tangent is opposite over adjacent, so it's just going to be x over the cube root of 3, opposite over adjacent, it's going to be the square root of x squared minus 3 over adjacent, the square root of 3. Now, theta, we can do this in a couple different ways. We could just do it from here. We would know that theta equals these things, or let's use ones that don't involve so many, like let's use one that doesn't involve the opposite side since it has that radical and if there's a lot more going on. We could also say that cosine, or you could really use any identity, it does not matter. I'm just going to use cosine. I know that cosine is equal to adjacent over hypotenuse, so the cosine of theta is going to equal the cube root of x. Now if I'm trying to solve for theta here and plug that back in, I have to do the inverse of cosine, so I know that theta is going to inverse of cosine each side, or arc cosine. It's going to equal the arc cosine of the square root of 3 over x. You could have used any relationship. If you wanted to use sine, that would be fine. I just chose cosine. So we have these values in terms of x. We can go ahead and plug those back in. Okay, and I guess if this was an indefinite integral, we would have a plus c. But what we're going to do, and I'm going to do this in red now, is we're going to actually take what we found this definite integral to be. We're going to plug in our values that we know are in terms of x, and then integrate that in terms of our original limits of integration, which were in terms of x, rather than having to convert everything. So we're going to have the cube root of, well, tangent theta in terms of x, we know is the square root of x squared minus 3 over the root 3, minus theta, and we found theta to be arc cosine of root 3 over x. And since we have everything in terms of x, we know, I guess I could write, and I should have written, that the integral from the cube root of 3 to 2 of x squared minus 3, cube root of that over, or square root of that over x. I've been saying cube root, and I don't mean to. I mean to be saying the square root of 3 times dx. Well, that's equal to this. And I'm going to move this so it's not so clumped together. Move this up a little bit so it's also not so clumped together. Make this a little bit neater. All right, so we know it's equal to this. And then, well, our limits of integration, since we're in terms of x again, we can use our original limits of integration. This is going to be from the square root of 3 to 2. And if you plug this in your calculator, you should get, well, substituting in 2, you're going to get square root of 3 over 3 minus pi over 6. Then you plug in the cube root of 3 for this, and you subtract that. That's going to be equal to 0. We're taking that times the cube root of 3. Just plug that in your calculator. You should get about 0.931. So your book shows you a technique on how you could change the limits of integration. I argue that that involves a little bit more work, at least for me personally, maybe, because you have to consider certain cases for theta values. So I prefer just to keep everything in terms of x before we do those, before we actually evaluate those using that fundamental theorem of calculus to evaluate that definite integral. Okay, now that's how you would tackle this kind of problem. You don't have to convert the limits of integration. For certain problems, though, however, kind of like we've done before when we were doing integrals involving square roots and things like that, you might have to complete the square again. So, for example, if you have like the integral of the square root of x squared minus 2x dx, you'll notice you don't just have some constant value. So we're going to complete the square there. You're going to take your linear term, whatever this is in front of this x here, divide that by 2, square it, both add and subtract that value, and then kind of continue that process of completing the square. Eventually you would end up with something like the integral of, now we have the square root of x minus 1 squared dx, which is something that we can now use, and it's in the form of u squared minus a squared, or whatever it might be when you're completing the square. So keep in mind that you might have to complete the square on some of these, so make sure you're brushed up on that. Okay, now your textbook gives you special integration formulas for these. So if you have something like these, you can know, and this is not something that's going to be super easy to find, you can just plug these into the formulas you have here. If you ever forget these formulas, which you probably will, you don't need to have them memorized. You can always just do integration as if it were some trig substitution like we've been doing, and you'll still arrive at the correct answer. This is kind of just a shortcut if you can commit these to memory. Okay, well this is going to be equal to 1/2 the integral of the square root of a squared minus u squared du. Remember that u is going to involve some variable. Is equal to 1/2 times a squared times arc sine u over a plus u times the square root of a squared minus u squared. And since this is an indefinite integral, we're going to have some constant being added at the end. Okay, if you have the square root of u squared minus a squared, your answer for an indefinite integral is just going to be 1/2 times u times the square root of u squared minus a squared times the natural log of u times the natural log of the absolute value of u plus the square root of u squared minus a squared plus c, where u has to be greater than the value of a. And our last one, if you have the integral of the square root of u squared plus a squared du, that's equal to 1/2 times u times the square root of u squared plus a squared times the natural log, the absolute value of u plus the square root of u squared plus a squared, close that absolute value, close that parenthesis, and then plus some constant c. Okay, that was a lot of things going on, but we have these formulas. You don't need to memorize them because you can always find these by doing some trig substitution. But it's going to come in handy if you can recognize that, and you can just plug in your a values and your u values and make that a little bit easier for yourself. So we're going to find the arc length of a function here. Excuse me. So we want to find the arc length of the graph of f of x equals 1/2 x squared from x equals 0 to x equals 1. So remember that the formula for arc length, to find arc length, it's given by, well, your limits of integration, whatever your interval is, a to b, in this case it'd be 0 to 1, of the square root of 1 plus the derivative of that function squared, or f prime of x, that quantity, squared dx. And that's how we can find arc length. So, well, let's just look at what the graph of this looks like. I graphed it on Desmos. Here's what we're graphing. Now this is the function 1/2 x squared, but if we limit that to the interval x equals 0 to x equals 1, it's going to look like this. So we want to find this length of this arc this arc length, basically this portion of that parabola. So we just use our formula. We know that the arc length is going to be equal to the limits of integration. Well, we're going from 0 to 1 of the square root, and we're going to need to find f prime of x. Let's just do that on the side here. And that's a pretty easy derivative to find. Take us back to the glory days, the early days of calculus when we were just doing nice, easy derivatives. What's the derivative of 1/2 x squared? Well, multiply by that power, subtract 1 from that power. We're going to get 1/2 times 2, which is 1. So just x to the 2 minus 1, which is 1. So just x. That one's pretty easy. So plug that in. We're going to get the square root of 1. Whoops. I want to make sure I'm still in the same color here. 1 plus x squared dx. And you should be able to recognize, well, this is in the form of the square root of u squared plus a squared du. Because, well, dx is the derivative, is what you would just get if you did the derivative of u. So, excuse me, it's almost what you would get if you did the derivative of u, but you should recognize that this is in the form of u squared plus a squared du. Okay, so what we can do here Whoa, not what I wanted to do. What we can do here is use this formula here. This is the one that its pattern is recognized. We would recognize that u squared, well, our u value would be x. du, well, if u is x, then du has to just be 1 dx, so we're good there. We can just plug things into this formula here. So we're going to do that. We know that this is equal, this integral, and it's a definite integral, so keep in mind we're going to have to do some integrating. Well, it's equal to 1/2, and that's a constant, so we could just multiply that out front. 1/2 times u, x, times the square root of u squared, well, x squared plus a squared. Our a is 1, so that's just going to be 1, plus a squared, well, that's just 1 squared, 1. We don't really need that. I'm going to leave that there. Times the ln, the natural log, of the absolute value of u, x, plus the square root of u squared plus a squared, well, x squared plus 1 squared again. Close that absolute value sign, close that parenthesis, and it would be plus c if it was a indefinite integral, but we're doing a definite integral. So we want to, close my parenthesis there, we want to evaluate this from our limit of integration 0 to 1. Okay, so all I'm doing is using that formula, makes integrating faster because that's what I'm going to get in the end. Anyways, if you just wanted to integrate this using trig substitution, you certainly could. You should arrive at the same answer. But we're going to find that this is equal to approximately, if you plug this into your calculator, you should get about 1.148, and that would be our arc length. So that one's not too bad. Okay, so that's all we're going to cover in this section of notes. Pretty brief. Make sure you're working on that progress packet, working through those problems, ready to go, and have a good weekend, everybody. Have a good break. We don't have school Friday or Monday, and I will see you when I see you. Have a good day, and as always, stay safe out there.